Hello everybody, I'm Wojtek Czerwiński and I will tell you a few words about our recent results about reachability problem for vector addition systems. So this is a joint work with Łukasz Orlikowski, and here I will focus on recent lower bounds for fixed dimensional vector addition systems, which I abbreviate as VASSes. So first, what is a problem we consider? So the reachability problem is the following. You are given a vector addition system with states, which I abbreviate as VASS. So what is a VASS? A brief reminder, it's an automaton with a bunch of counters. Here we have 3 counters, and these counters can be decremented, incremented. They cannot be tested for 0, and they cannot go below 0. And we are given 2 configurations, S and T. Configuration is just a state and counter evaluation. And the question is there a RAM from this configuration S to this configuration T in our VASS V? Okay, so that's the problem. There is a long research history about this problem since 70s, but I will tell you only briefly about recent history, because this is our context. So in 2019, Jérôme Leroux and Sylvain Schmitz, they have shown that the problem can be solved in Ackermann time. And then it was only known that the problem is X-space hard regarding lower bounds. So then in the same year, we have shown with his co-authors that the problem is tower hard. But still a gap remained. And last year we have, so like 2 teams independently. One team, Jérôme Leroux, and another team is we. So me with Łukasz Orlikowski, we have shown independently that the problem is Ackermann hard. So actually, together with Ackermann upper bound and Ackermann lower bound, joining it, we know that the problem is Ackermann complete. So the question is, yes, like, is everything solved about this problem? So on one side you can say yes, but there are still many interesting problems around. So first of all, you can consider the reachability problem or other problems, but reachability problem for vectorization systems, for generalized vector addition systems, like with stack or branching vector addition systems or with data and so on. But today I want to tell you about something else, which I find very interesting. I think there is still some mystery hidden there, and we still lack some fundamental understanding. So these are low dimensions, small dimensions. So maybe what is known, so for 2-dimensional VASSes, this is how I abbreviate it, like 2 VASS in dimension 2, it's known that the problem is, reachability problem is p-space complete. But what about dimension 3? Already here we have a huge gap. So we have p-space hardness, because 3 is bigger than 2. But regarding upper bounds, we only know that the problem is in so-called complex class F7, in fast-growing complexity classes. So this is more than tower of exponential. So yeah, so we don't know whether the problem is p-space or maybe triply exponential or tower or even higher. And here on this example, you can see that we really lack understanding. And if we consider like any dimension, that this lack of understanding is blurred. But we lack, I think we need more research. And you can ask other interesting questions here around, like for which dimension D, for example, the problem is elementary. Yes, so exponential, double exponential, or something like that. So yeah, so our experience in this area of VASSes shows that often considering small dimensions, it leads to developing some interesting techniques, which then lead to solving the problem in general or making a progress in the general case. So probably considering small dimensions, it's just easier to design a technique there. So this is why we looked at small dimensions, and also we think that small dimensions are actually interesting. This problem for dimension 3 seems natural. So this is our result, the following theorem. The theorem is that the reachability problem is, first of all, it's NP hard for 3-dimensional VASSes which are unary means that transitions are encoded in unary, and flat is some subclass. I don't have time to tell what subclass. So this point is actually progress with respect to LICS. In LICS, we had dimension 4. We managed to improve it. The problem is also p-space hard for unary 5-dimensional VASSes, X-space hard for binary 6-dimensional VASSes, and tower hard for unary 8-dimensional VASSes. So I don't have time to tell you more about this. So these are progress. So all these cases, they form some progress with respect to previous knowledge about this. Maybe I want to make one point. What were our techniques? So we have used 3 techniques. One technique is controlling counter. So this is a technique which we used with Łukasz in our Ackermann hardness paper. And we used it in these results. So here we have 4 points in our theorem. So this controlling counter technique was used in point 1, 2, and 4. Another technique is multiplication triples. It was already used in tower hardness paper. So it's used in results 3 and 4. And we designed also another technique, which is a new one. We called it quadratic pairs. And this is used in results 2 and 3. So what is maybe interesting that we actually needed 3 different techniques for, essentially speaking, the same thing. So there is no one dominating technique. Yeah? So we needed 3 incomparable ones. So this seems interesting. Maybe we still don't know the technique. Okay, so last slide was our message. I think the main point is that we need to study low dimensions. It's worth to study low dimensions. And another point is that we design a new technique and new combination of techniques. So if you are interested in this field, you can look at our paper on archive, and I would be happy also to discuss with you. That's all. Thank you very much.